Okay, so I think Ronno, we are ready to
Okay,
start.
I'm ready.
Okay, so welcome everyone. We are very happy to have Ronno Das from University of Chicago today, and he will speak about non-collinear points in the projective plane. Please go ahead, Ronno.
Yeah, thanks for the introduction and thanks for the invitation. I'm sorry we had to reschedule because of natural disasters. Okay, so yeah, I'm going to talk about, as Krishna said, the space of non-collinear points in the projective plane, and all of this work is joined with Ben O'Connor. Yeah, so let's start with the setup. So we're going to have n points. I'm going to call them P1 through Pn in the plane. And the condition I want on these is that they're not just arbitrary points. You cannot have 3 of them on the same line. So obviously, any 2 of them would be on a line, but you can't have more than 2. So now there's there's a couple of points about what plane I'm looking at. And sorry, 1 second. Yeah. So we could start with like the real plane, but there are a couple of issues here. One is that in just the real plane, we have this issue of parallel lines versus non-parallel lines, and that's going to sort of cause problems in the combinatorics. So the fix for that is going to be to pass to the projective plane. So then all pairs of lines are the same. There are no parallel lines. This doesn't quite eliminate all these issues. You're still going to have that triples of lines are not all the same. And that's sort of fundamental. That's like a fundamental problem that we cannot really escape in our results. So I'll sort of talk about that at some point. But for now, let's just avoid issues by going to the projective plane. Second, we want to look at the space of all the endpoints satisfying this condition. So if we look at over R, this is given by some set of inequalities. Well, really, we are saying that 3 points are not on a line if some determinant does not vanish, but you're over R, so you can sort of break into cases whether the determinant is positive or negative. And so essentially, this space will break up into pieces, and each piece will be convex because they're defined by inequalities. And the problem with a convex space is that's not interesting topologically. That's just all the pieces are contractible. So it's just like at the level of topology, I want to think about the space that's just going to be like a discrete set of points, and that's not interesting. So instead, we are going to pass to complex numbers. And this complicates the problem, but at the same time, it makes it interesting and sort of has other connections, and we are going to exploit those connections. So this is ultimately a very good thing. Okay. Yeah, so this is going to be my space. X sub n is the set of n tuples of points in the complex projective plane, so that no 3 are collinear. And in case you're not super familiar with the projective plane, a line is literally a solution of a linear equation, and so that's a copy of the projective line. Okay, so this is a space, but we don't want to just, so when you're studying a space, it's always good to keep track of what symmetries that space has. And that sort of helps, and also is like, it's not just the space by itself, that's like that should be part of the data. So what are the symmetries of the space? Well, I chose my space to have tuples of points, so I can obviously reorder them. I chose a labeling of the points P1 through Pn. I can switch, say, P1 and P2. Maybe you don't want to think of that as a separate collection of endpoints. So there's this choice of ordered versus unordered, or labeled versus unlabeled. And that's essentially given by an action of the symmetric group on n letters permuting the n coordinates of this tuple. So you might care more about the quotient by this Sn. I'm going to call that space Y sub n. And sort of whatever problem we solve, we'll solve it in a way that this quotient, you can sort of pass to the quotient without much effort. Okay. The second symmetry that sort of is important here is the one that's symmetries of the plane. So in R2, you should think of rotations and translations, reflections. But in CP2, so this is essentially by, so points of CP2 are, vectors in C3 up to scalar multiples. So there's an action of GL3, the general linear group of 3x3 matrices. It's non-singular 3x3 matrices. And if you take a vector and a multiple of that vector, their images are also multiples of each other. So that's an action on the projective plane. And scalar matrices just scale each vector, so they don't change the line, so they act by identity, which means that you actually have an action of the projective linear general linear group, or PGL3C, which is just the quotient by scalar matrices. Okay. Yeah, so this action on the plane, it's by linear thing, so it takes lines to lines. And so if I had a bunch of points that were not on a line, then they're still going to go to some bunch of points that are not on a line. So this action will be an action on Xn. Okay, so this is more or less a setup. And then we have some facts. So any questions so far? Okay. So this action, it turns out, is fairly easy to understand, the second action by the symmetries of the plane. And the fact is that, well, on X4 in particular, this action is simply transitive, or as I say, it only the identity element of the group will fix a point, and any point can be taken to any other point. So what that means is, what that's going to mean is that my X sub 4, which is a set of 4 points on the plane, so that no 3 are collinear, is going to be isomorphic to PGL3. So this is really PGL3C. If this fact sounds new to you, this is maybe you're more familiar with the fact that if you look at the PGL2 action on CP1, this is about the Mobius transform acting on the Riemann sphere. That's determined by 3 points. It acts simply transitively on 3 tuples of points on the Riemann sphere. This is exactly the analog of that, one dimension higher. You need just like you needed the 3 points to be distinct 3 points there, you in the plane case, you need no 3 to lie on a line. This also generalizes by the same proof as I'm going to give below to the action of PGL PGL n plus 1 on CP and choice of n plus 2 points. Okay, so yeah, every talk should have one proof. So this is going to be the one proof I give in full detail. Well, not full detail, but some detail, is that this action is simply transitive. Saying that the action does not have fixed points and takes any point to any other point is the same as saying, if you give me 2 points in the space, there's a unique element of the group that takes the first one to the second one. So that's exactly this first characterization, given P1 through P4 and Q1 through Q4 both, so that no 3 are on a line. We want to show that there's a unique matrix up to scalar that takes the first tuple of points to the second tuple of points. So this is not so hard to prove. This is essentially linear algebra and so easy linear algebra. So you think of these points as actually just, take representatives in complex 3 space. That they're non-collinear will imply that any 3 will be linearly independent, in fact. So, and it's again like an easy exercise that I don't need to do this for arbitrary tuples of points. I can choose my first tuple and then just say I can move that to any other tuple uniquely. And so I can choose my first tuple to be the 3 unit vectors and then the sum of the 3 unit vectors. So if you do that, so that's my choice of PIs. And for QIs, because they're linearly independent, any 3, I can write the fourth one as a linear combination of the first 3 with the additional constraint that none of the coefficients can be 0. So for example, if the if the coefficient of Q1 was 0, that would mean that Q2, Q3, and Q4 all have first coordinate. So that would mean Q4 is in the span of Q2 and Q3, which if you sort of translate to the projective plane tells you that those 3 points are in the same line. So you get that all these coefficients are non-zero, and then you can just take the matrix xq1, yq2, zq3, so the 3 sort of summands of this linear combination. And it's also not hard to check that you have to take this matrix up to a scalar multiple. Yeah, so that proves that there's a unique matrix that takes P1 through P4 to Q1 through Q4. And so that proves this simply transitive statement. So as I said, a corollary of this is that my fourth, in this infinite family of spaces I'm considering, the fourth space is exactly the same as PGL3, which we understand quite well. In fact, you can apply this argument generally to Xn, just apply this to the first 4 points. And what that tells you is that my space Xn factors as a product of this group times the quotient by this group. So again, this group is easy to understand. So essentially understanding Xn reduces to understanding the quotient. So this quotient is, I'm going to call this F sub n, and it turns out that it's also the same as fix the first 4 points, P1 through P4, and then look at the possibilities for points 5 through n. So Fn is isomorphic to this space, P5 through the space choices of 5 through n, so that the first 4 are some chosen points that that are allowed. So I chose again the first 3 unit vectors and the sum of the unit vectors. Okay. If this is somewhat mysterious to you, that here I have a quotient, but then here I have something that looks like a subspace, this is essentially, so I'm not going to explain this in detail, but the point is that this quotient xn to fn is a PGL3C bundle. By the simply transitiveness before, this is a principal PGL3C bundle with a section. And now the other project, so that tells you that xn is the product of PGL3 and fn. And so I can switch the 2 factors to get a map to PGL3C, and the fiber will be the same as fn, but then the map you choose is the projection to the first 4 points, because I know the first 4 points is the same as the group. So it's sort of a, if you're familiar with sort of how this principal bundle with a section is a product, then this is sort of easy to see, but otherwise it's like a confusing thing. So I'm not going to explain this in full detail. Okay. Questions so far? All right. Okay, so now we are ready to state our theorems. So theorem 1 is we compute X6 fully with the S6 action. Well, I don't compute. So what do I mean by compute the topology? We compute the cohomology of the space with rational coefficients. So as I'm going to say right below this you should think of as like a linearization of topology ignoring torsion. So we are computing the topology with the S6 action. Well, this is sort of this is what we can do. Theorem 2 is this product that this corollary that this xn splits as a product. There's also a version of this with the Sn action. And in cohomology, that takes the form of tensor product. So you get that cohomology of xn is the tensor product of cohomology of PGL3 with the cohomology of the quotient. And this is true as vector spaces from just the base level product. Yeah.
What is the action on S star of PGL3?
Yeah, it's trivial.
Oh, okay. Okay.
Yeah. Good question. I didn't want to sort of clutter the statement, but it's trivial. That's the maybe non-trivial thing to show, is that you get the correct answer by acting trivially on the first factor. There is no Sn action on PGL3C that's going to be compatible with this picture, except for n equals 4, where its action is trivial.
And your description of Fn kind of breaks the S and symmetry, right? So
yeah, so I'm not saying I'm going to think of Fn as the quotient, but it happens to be isomorphic to this subspace.
okay.
Yeah. Okay. Yeah, so the quotient has an Sn symmetry that's not so hard to see. If you take n points and move them by PGL3, and you permute the points, you're still going to get a permutation of the moved points. So the quotient gets an induced SN action. And that's the SN action on the cohomology here. Okay, other questions? All right, great. And by an explicit computation, I mean we can write them down as like irreducible decomposition of the representations. So maybe one point to make here is that I'm saying we only have explicit computation of x6. Well, I'm gonna say this later in more detail, but above 6 is hard for reasons I'm gonna explain. Below 6, 5 was known before, but maybe not in this form, but sort of something equivalent to this. 4 is easy just from our description of it being equal to PGL3C. 1 and 2 are really simple. You can like write down those spaces without much effort. 3 is maybe not trivial, but sort of if you know the things that go into computing cohomology, I can explain it to you in like half an hour, like the whole computation. It's not anything, like I can give you all the details in like half an hour. Okay. So before sort of talking about the proof, I'm going to talk about how these statements connect to other things that people are interested in. This space does seem sort of fundamental to me, at least. Just like, you know, we care about distinct points, or like collinearity of points is like a fundamental thing that we talk about starting from high school. So sort of just the space of non-collinear points is, at least to me, is fundamental. I mean, maybe that's not a good justification that we talk about some things in high school that are not mathematically very interesting, but this also turns out to be interesting. Okay, so yeah, so if you look at x5, that's like the choice of 5 points so that no 3 are collinear. It's maybe the first result one learns about result of this type that one learns is that there's a unique conic, smooth conic section passing through any such choice of 5 points. This is not hard. The space of conics is 5-dimensional, and sort of forcing it to pass through each point is going to cut down your dimension by 1, and they're all independent conditions because no 3 are on a line. So you get some finitely many points showing that it's 1 is not so hard. Conversely, if I choose 5 points on a smooth conic, by Bezout, no, you can't have 3 of them lying on the same line. Otherwise, the line would be contained in the conic. And if I have a smooth conic, you can't have the line be contained in the conic. So that tells you that 5 choices of such points are the same as 5 points on some conic in the plane. But if I'm allowed to move around by symmetries of the plane, all conics are the same. I can move any conic in the complex projective plane to any other conic. So that's just saying I have 5 points on some conic. So what that tells you is that, so therefore, if I go modulo this PGL3 action, so this is F5 on the left, that's the same as just 5 points on a conic, 5 distinct points, modulo the orthomorphisms of the conic. This, since a conic as an algebraic space by itself is the same as a P1, this is the same as the moduli space of 5 points on a genus 0 curve. So this also sometimes denoted as M05. So like I said, X5 was computed by before, and it was essentially as M05. Kissin and Lehrer have this paper from, I believe, 2014, where they compute the cohomology of M0n for all n, essentially using the same methods as us. Okay, so that was X5 specifically. What about other n? So if I look at x6, if I insist that my 6 points not only are no 3 on a line, but also not all 6 on a conic. So there's one conic through 5 points, but for general 6 points, there's not going to be any conic through that. Then you get that. So people are also interested in such configurations of 6 points. And one of the reasons is because if you blow up your plane at those 6 points, then you get a smooth cubic surface, and conversely, every smooth cubic surface you get this way. Sorry, this should be equivalent to x6 mod PGL3. See, so the moduli space of smooth cubic surfaces is the same as f6. So our quotient of x6 by the symmetries of the plane. Well, sorry, no, it's not equal to. It's like an open locus in this. Don't know how that went away. And the reason it's not the whole thing, but an open locus is because the left side has this extra condition that the 6 points are not all on a conic. And so the complement is going to be 6 points all on a conic. So we also understand that because that's by the same description above M06. So choice of 6 points on the conic. And so knowing things about x6, because we already know things about M06, also gives us facts about, like, it also gives us the cohomology of moduli space of smooth cubic surfaces. Except we only know the right side with an S6 action, and the correct group of symmetries of the left side is not just S6, but the wild group of type E6, which is a 72 index supergroup of S6. So there's sort of more data that you want on the left side that you don't quite get from the right side. And there's a paper of Bergwall and Gunadas that essentially finishes this computation by, again, using the S6 version. Okay. Similarly, for n at most 5, this extra condition of not being on a conic does not appear. So those are literally the same as moduli space of del Pezzo surfaces of degree 9 minus n. If you know what del Pezzo surfaces are, this should make sense to you. Otherwise, just ignore that, the thing in blue. Okay. Yeah. So this is sort of, so the point of these two connections was that these spaces are well related to other moduli spaces that people are interested in. Okay. So now we're going to look at, so we've been working over complex numbers. I sort of started with this justification of why Rn is not important topologically. Now we'll look at the case where the topology is obviously not interesting. All the sets are going to be finite. Well, and we'll see in a few minutes that this is quite intimately connected with the complex case because of reasons I'll come to. Okay. So the point is I can define these spaces over any field. It should be any, not an. So it turns out that if you look at it up to so if you ignore the S6 action, that doesn't change so much. It's like a factor of n equal 6 factorial. The number of points over the finite field FQ. So instead of looking at the field of complex numbers, we're now looking at the finite field of size Q. So if Q is a prime power. If it's prime, then it's Z mod P. But if it's not prime, then it's some finite extension of Z mod P. So if you look at the number of points over a finite field, n points, so that no 3 are collinear, it turns out that this number is polynomial in Q. So we are looking at this as a function of Q. So it turns out this is polynomial in Q for n at most 6. This is not so hard to check. You essentially just count them, adding 1 point at a time. and you get that it's polynomial. For n is 7, 8, or 9, it's quasi-polynomial. Well, what does that mean? It means depending on the residue of q modulo some fixed number, for n equals 7, that fixed number is 2. So it just depends on whether q is odd or even. So if the characteristic is odd or even, you get that it's one of, so if it's one polynomial for q odd, one polynomial for q even. And then there's, I think for n equals 8, there's like 6 choices, something like that. Like q mod 6, it depends on. And so the reason for this quasi-polynomialness is essentially, so for n equals 7, the reason for this is the Fano plane. So the Fano plane is this picture where you'll have 3 lines, and then you have 3 other lines, sort of think of them as medians to this triangle. But then it turns out the 3 points on 3 base points on the 3 sides are also part of one line. So this configuration doesn't exist over R2, so I have to draw that 7th line as a circle, but it does exist over a field of characteristic 2, and so that shows up in the count somehow. You have to adjust for this configuration being possible or not possible, so you have to care about whether q is 2 or not, even or not. And in the same way, for n is 8 or 9, you have to care about other configurations that can only exist over certain characteristics. 7 and 8 are still sort of, you list these, and it's not so hard. You can do this by hand. For n equals 9, this is a result of Yampolskaya, Skorobogatov, Sorokin, and I think they were looking at some sort of they were looking at this problem from some coding theory aspect. Somehow having non-collinear points corresponds to some sort of binary codes, and they computed this count in that context, but it's equivalent to this. And then by work in progress of 6 authors, for n equals 10, this count is not even quasi-polynomial, so it just has things that are not polynomial in Q. And if you're interested and as to why this occurs, well, I'll sort of argue later that we expect this to occur eventually, like anyway. But in this specific case, I believe the topology picks up some elliptic curves and some K3 surfaces which have point counts that are not polynomial, and so that shows up in the, like, these are related to some moduli spaces, and it turns out that the relevant space here is isomorphic. There's like strata, one of them is isomorphic to or maybe a couple of them are isomorphic to some non-trivial elliptic curves, and one of them is isomorphic to a K3 surface, and then yeah, but I don't know all the details. This work is still sort of, it's not written up yet. Okay. Yeah, and now I mentioned this in the abstract. I'm not gonna explain why this is arbitrarily complicated, but there's a somewhat well-known result that the configurations that you have to deal with in computing this very fundamental space can get arbitrarily complicated, the combinatorics. So specifically, if you just have 6 points, well, they can pairwise give you 3 lines. There are more lines that I haven't drawn, but if I just focus on 3 of the lines, well, those 3 lines can themselves be collinear, concurrent, so pass through the same point without any of the 3 points of my 6 chosen being on the same line, as you can see in the left picture. However, if I just perturb those 6 points by a little bit, I'm going to get a configuration of lines where those lines are not passing to the same point. So this tells you that all the configuration, so this sort of X6 is not just, so why does this matter? So if I want to add a 7th point to these 6, well, that has to not lie on any of these lines. So the choices of my 7th point is going to be different in the left picture and the right picture. in the right picture, there's this, I mean, over R2, this is sort of visibly clear that there are different number of components, but it also shows up in over complex numbers, and it's in a more complicated way. And this problem only gets worse as you get n higher and higher. It doesn't get any better than this. So yeah, like I said, this gives you different choices for the 7th point given the first 6. And it turns out that the combinatorics of these strata can get, strata just is like a fancier word for pieces, I guess. So there's this result called Niev's universality, which tells you that the combinatorics of these strata will be arbitrarily complicated. You can embed an arbitrary matroid into the matroid of non-collinear points, and it turns out that that means any algebraic relation can be encoded into this combinatorics. So you expect the topology of an arbitrarily complicated algebraic variety to eventually show up in the topology of Xn. There's a somewhat expository, some new results paper of Vakil on the paper is known as Murphy's laws. The title is Murphy's law in algebraic geometry or something. So research, which explains how this universality result applies to inducing polynomial relations, encoding polynomial relations as collinearity. Okay. So yeah, that's so what this means is we should expect the problem of n large to be as hard as it can be. So if you could solve this problem for xn, I mean, this is not a quite proof because this is just talking about the strata, and it could just miraculously happen that all of this complication in the different pieces somehow cancel out when you're talking about xn, but that just seems unlikely. And I mean, there's not a proof, but it would be very surprising if those cancel out exactly, and xn was always something that's nice and describable. And maybe evidence for that it doesn't always cancel out is this not quasi-polynomial result for n equals 10, which shows that it's already complicated for n equals 10. Okay. So we can only go up to 6, but maybe that's like there is some fundamental barrier at some point. Maybe we are not quite up against that, but we are up against some, like the first instance of that barrier in our theorem. Okay, so now I'm gonna explain how one proves such a result. And essentially the basic idea to the fundamental thing we are gonna exploit is the connection between cohomology of the complex version of some algebraic space versus the point counts of the finite field version of that space. This is one of the seminal works of the 20th century, Deline's proof of the Weil conjectures, along with certain comparison theorems between cohomology of the complex points with the finite field point, data cohomology of, and then the cohomology of the finite field points. And what the usual application of this boils down to is that if you have enough information about the cohomology of the complex points, and by enough information, I don't just mean the Berry numbers, but you need to know something about the classes. Maybe it's sometimes enough to just know where the classes come from. If you
have a question, yeah. Your spaces are not compact, right? Yeah.
So you have to do, but they're smooth, so you can use Poincare duality to switch to the compactly supported cohomology, and then it's okay. So maybe I can say the usual form is with compactly supported cohomology.
Okay.
Yeah. Okay. So yeah, right. But good point. Thanks for the comment. So yeah, so the usual form this takes is you know enough about cohomology, and then you can predict what the points counts are going to be. So we are going to use a backwards version of this, which is if you know you're in a good situation, which I'm not gonna write down what good is, but maybe I'll explain orally. So if you already know that the cohomology is not going to be bad in some sense, then you can reverse the arrow. You can go from the point counts to the cohomology, and that's essentially the idea. So first, let me explain what I mean by good, or sort of why the spaces are good. So what I'm going to use as good is essentially our cohomology we know will be generated in degree 1, and we know that the degree 1 classes have weight 1. They come from, they are isomorphic to cohomology of C star, the class in cohomology of C star, the generator. So you know how Frobenius acts on that class, essentially. Okay, so why are our spaces good? And the fact is that if I take n points of that no 3 are collinear, and I forget the last point, so I had n points, but then I only look at the first n minus 1, those are still going to be, no 3 of the first n minus 1 are going to be collinear. So I get a map from xn to xn minus 1. And for n at most 6, this is a fiber bundle. So what that means is the space of choices for the 6th point does not depend on, depends continuously on the first 5. So this sort of difference does not happen for n less than 6. So the choice of this up to the 6th point is continuous. So that's not quite enough. We also know what is the choice of nth point given the first n minus 1, where n is at most 6. Well, it's exactly the projective plane and then you cut out all the lines that you already have from the first n minus 1 points. If my nth point is not to be collinear with any of the first n minus 1, any pair, then that's exactly saying it's not lying on one of those lines. So you're taking the plane and then you're cutting out some lines. This is lines in the plane are hyperplanes. So this is a complement of hyperplanes, or a hyperplane complement. And a lot of things are known about hyperplane complements. What's relevant for us is that their cohomology is generated in degree 1. They're generated by classes pulled back from essentially a hyperplane in some complex dimensional space, which is the same as the hyperplane in one-dimensional complex space, so the 0. And these classes are sort of the best one can expect in this context. For example, this follows from Gorski McPherson, who give like a complete presentation of the cohomology algebra for hyperplane complements, and maybe in some more generality. Okay. So, yeah. Yeah. So, given that this is a fiber bundle, one could ask the question, well, this should be already enough to compute cohomology. We know a lot about cohomology of fiber bundles. There's a reasonably useful spectral sequence for the, once I know the fiber bundle and I know the base and the fiber, well, I already said I know the fiber. The base we know inductively, so this should be enough to compute cohomology of the total space, xn in terms of xn minus 1. Well, it is, except, so you can compute the Betti numbers this way. You have to deal a little bit with the differentials, but you can do this. It turns out, so the issue with this is we want to compute the topology of xn with the Sn action. And this map is, when you forget the last point, you're fundamentally breaking the Sn symmetry. You're only keeping the Sn minus 1 symmetry. So you don't get the cohomology of xn as an Sn representation. You get it as an Sn minus 1 representation. And then your induction doesn't work because you only would know xn minus 1 as an Sn minus 2 representation. So if you want to keep track of the group actions, then the induction doesn't work. So that's why we have to go to this point count version and then come back to cohomology. Well, how do we keep track of the SN action on point counts? So we need a somewhat finer version of this point count cohomology correspondence. Specifically, we want to know, so this quotient by S. So if we want to know the SN action on cohomology, what you need to know on the point count side is you go to the SN quotient of your space. So that's this XN mod SN SN. You look at its FQ points, but you're going to have you're going to have some things in that come from not just FQ, but finite extensions of FQ. And I'm going to explain that in a second. So you have to know how many of those points come from what finite extensions and sort of in what pattern. So that's like the action of Q with Frobenius, which is the map X going to X to the Q, on points of this quotient space coming from finite extensions. So why do I have to look at finite extensions, and sort of what does this mean that it comes from, that a point of this space over FQ comes from finite extensions and not just FQ? So what is a point of the quotient defined over a finite field? Well, it's not take the points that are defined over that finite field and go modulo the group action. It's you're allowed to take orbits of the group, which as an orbit are defined over the finite field, but each individual element of the orbit might be defined over some extension. So you look at all choices of points in all finite extensions at the same time, you go to the orbit space of that and see which orbits are defined over your finite field. So you go in the quotient and then you look at what orbits are defined. So that's like taking points that are fixed under X going to X to the Q, so, or Frobenius Q. If you're not familiar with this, you should compare this with the real and complex case, where the polynomial x squared plus 1 is a real polynomial. So its roots are not defined over real number. They're plus or minus the imaginary unit. But the pair of roots as a pair is defined over R, because I can define them as the roots of x squared plus 1. And the polynomial x squared plus 1 is defined over R. So this is corresponding to pairs of points defined over R are pairs of complex numbers that are invariant under conjugation. So it could be two individual real points that are individually invariant, or it could be a pair of points that are switched, and that's also a defined pair. So it's sort of the same picture, but over finite fields, where instead of complex conjugation, you have this Frobenius Q. Okay. Yeah. So, and because FQ, the algebraic closure is just the unit of finite extensions, every such thing is going to be defined in some finite extension of FQ. So we need to look at points defined over finite extensions, and then orbits of those by under the symmetric group. What we finally need to count is, so look at all sets of, say for n equals 6, all 6 tuples of points defined in some finite extension. And then if I apply Frobenius or the conjugation, they're going to be permuted in some way. Well, 6 points are being permuted, so they're going to be permuted by some element of S6. I want to count for each conjugacy class of S6, how many 6 tuples are permuted by that some element of that conjugacy class. Well, why conjugacy class? Because this choice of permutation is not really defined canonically. It's only defined up to conjugation. And this, if you're a topology-minded person, you should think of this is like choosing a base point, and like there's a pi1 thing happening, or it's just choosing a different algebraic closure if you're sort of more algebraically minded. You're choosing all the finite extensions at the same time, which is essentially the same as choosing the whole algebraic closure. Maybe you only need like a FQ to the 12 because for the n equals 6 case only, you need to only go up to degree 12 extensions. Or maybe degree 6. Okay. So what you do is, or what we do to prove our theorem is, well, we do a lot of counting over finite extensions of FQ, projective plane of that, and then for each conjugacy class of S6, which are indexed by partitions of 6, you have a set of a tuple of points which are permuted by that in that cycle type. So these partitions correspond to cycle. So this 4, 2 here corresponds to, there's 1 4 cycle of points and 1 2 cycle of points, and no 3 of them should be collinear. And I think in these pictures, we are abbreviating prob q by f. I don't know if it's how visible it is, but so for example, in the left, and then you have to avoid all choices of lines generated by the first, all the ways, you have to avoid all the ways that 3 of these can be collinear. So it's, as in often in combinatorics, it's easier to count the complement. So you count how many ways they can be collinear and subtract that. And so in this picture, because my points are defined over various finite extensions, the lines are going to be defined over various extensions. And so there's like a whole lot of just counting points on lines, drawing pictures of what ways lines can intersect, and keeping track of what is defined over which extension involved. But you do 11 of these cases given by 11 conjugacy classes of the symmetric group, and you come up with these counts. So in the pictures, for example, on the left picture, the thick lines are defined over a degree 4 extension, the thin lines are defined over degree 2 extension, and so on. So it's like you have to keep track of all this data. And you have to do it 11 times because there are 11 conjugacy classes. So you count all these polynomials. Well, then you equate them to then you plug them into the formula coming from this big algebraic geometry machinery of connecting cohomology with point counts. And what you have to do here is use a version of that that's defined for local coefficients. So going to the SN action is this. So the point is computing cohomology with the SN action is the same as computing cohomology of the quotient, but now with twisted coefficients twisted by SN. And then it turns out that the version of the trace formula, grothendieck trace formula you need here exactly asks you to compute the things I described before. And so you plug that into the formula, and then to compute the representations of S6, you use character theory. You know the character table of S6 is well known. It's like in Fulton and Harris, for example. This screenshot is not from there, but from somewhere on the internet. And you do all of this computation, plug that into formulas, and then just compute things, and then you get the theorem back, which is the number of the cohomology as representations of S6. Yeah, maybe I would like to end there. Thank you for attending.
Thank you, Ronno.
Yeah.
Please ask questions if anyone has questions. Okay, so maybe there are no questions.
Sure. Yeah. Yeah, thanks again for...
Okay, so thank you, Ronno, for a very nice talk. Okay, so thanks.
All right, yeah.
Take care.
Yeah, thanks everyone. Bye.